Good day, everyone. I am Jenemy C. Salva from BSED Math 3A. So today, we're going to explore my geometric model in the subject M115 Abstract Algebra. But before that, let me introduce to you first my geometric model. So this is my geometric model. I name it Octary Calyado Star. I'll give you some description of my geometric model. My geometric model is divided into two words, the word octaray and Calyado star. Let's proceed first to the word octaray. This word is also divided into two, the word octa and ray. So octa is a Greek prefix meaning 8, while ray it is refers to a straight line that starts from a point and goes off in one direction. While the word Calyado star is also divided into two words, the word Calyado and the word star. Kaleido comes from the kaleidoscope, which is a device that shows symmetrical, colorful patterns when rotated. And star refers to the overall shape of my geometric model since it looks like a star. And as you can observe, the color of my geometric model is purple because I do really love the shade of purple. And that is my background of my geometric model, Octary Kaleido Star. So now, let us proceed to the front and back of my geometric model. And as you can observe here, the front of my geometric model, I used letters, while, while the back of my geometric model, I used the Roman numeral number 1 until number 8. Now let's proceed to the moves that we have. For letter J, do nothing. Letter O, we need to rotate 45 degrees clockwise. For letter U, rotate 90 degrees clockwise. For letter R, we need to rotate 135 degrees clockwise. And for letter N, rotate 100 degrees clockwise. Next is letter E. We need to rotate 225 degrees clockwise. And for letter Y, rotate 270 degrees clockwise. And for letter S, rotate 315 degrees clockwise. And for the next one, we need to flip vertically and we will get the Roman numeral number 1. And next one is for Roman numeral number 2, we need to flip between right diagonal and vertical axis. And then we will get number 2 on the top. And for Roman numeral number 3, we need to flip about right diagonal. And then we will get this one. And for Roman numeral number 4, flip between right diagonal and horizontal axis. Then we will get this one. And for Roman numeral number 5, flip horizontally. Then we'll get number 5 on the top. And for 6, we need to flip between left diagonal and horizontal axis. Then we will come up with number 6 on the top. And for number 7, flip about left diagonal. And then number 7 would be on the top. And for the last, we need to flip between left diagonal and vertical axis. And as you can see, the Roman numeral number 8 is on the top. And here are the different moves that we have from letter J, O, U, R, N, E, Y, S. Number 1, 2, 3, 4, 5, 6, 7, and 8. Now, let us solve this one. So if you will operate J star J, we will get J. J star O, we will get O. J star U, U. J star R is equal to R. J star N is equal to N. J star E is equal to E. J star Y is equal to Y. J star S is equal to S. J star 1 is equal to 1. J star 2 is equal to 2. J star 3 is equal to 3. J star 4 is equal to 4. J star 5 is equal to 5. J star 6 is equal to 6. J star 7 is equal to 7. J star 8 is equal to 8. O star J is equal to O. O star O is equal to U. O star U is equal to R. O star R is equal to N. O star N is equal to E. O star E is equal to Y. O star Y is equal to S. O star S is equal to J. And we'll just continue operate the different moves. As you can see here, all the letters, we operate those letters. We have the letter R, N, letter E, and here letter Y, letter S. And from the Roman numeral number 1, number 2, number 3, number 4, number 5, number 6, number 7, and for the last one, we need to operate the Roman numeral number 8, and then we will record all the possible combinations that we operate. So this is the record of our possible combination if we operate the letters and the Roman numerals, and then we will get this table. Now, we're going to prove it if this table is form a group structure. But before that, let me define first what is a group. So when we say group, a group G is star is a set of G closed under binary operation star such that the following conditions are satisfied. So for G1, for all A, B, and C is the element of G, we have quantity A star B star C is equal to A star quantity B star C. And this is associative for star. And for G2, there is an element E in G such that for all E element of G is star X is equal to X star E is equal to X. This is the existence of the identity element of star. And for the G3, corresponding to each of the element G, there is an element inverse in G, such that A star A inverse is equal to A inverse star A is equal to E. And now, this is the existence of the inverse element for all element of G. So, now let us prove this first. So we have the element F the set of F consisting the element J, O, U, R, N, E, Y, S, 1, 2, 3, 4, 5, 6, 7, and 8. And this table represent a binary operation. This one is closed. It is because if we operate two elements, the results are always included in the set. And for checking the associativity of star or the G1. So in order for us to easily check if the table is associative, we will just simply rotate it by 180 degrees. And as you can see here, we will going to interchange some columns and rows. And here we will interchange the column 7 to 1. And next, interchange the column 6 and 2. Then, interchange the column 5 and 3. Then interchange the column S and O. Then interchange the column Y and U. And the last interchange we need is E and R. And after we interchange the columns 7 and 1, 6 and 2, 5 and 3, S and O, Y and U, E and R, we got the same structure with the original table. Therefore, we can conclude that the table under binary operation star is associative. Now, let us check if the table has an identity element. Okay, so in order for us to identify what is the identity element, we need first to locate the row that matches the element in the outer top row, and next find the column that matches the element in the outer left column. And in here, the element at their intersection is the identity element. In this case, as you can see, the intersection give us the letter J. So J is our identity element in this table. And for the next one, let us prove if all the elements has a unique inverse. Okay? So, in order for us to easily find the inverse element in the table, we need to start by finding the row of the element you want to inverse. Then look across the row until you find the identity element. The heading of the column where the identity appears is the inverse of the original element. So in here, as you can see, let us first locate the inverse of J. So in here, our identity element is J, as you can see, and J is in here. Therefore, the inverse of J is J. For the letter O, let us find first the identity element J in here. And here, as you can see, we need to look at the, the outer or the headings. Therefore, the inverse of O is letter S. And for the letter U, let us find the identity element J. And here, identity element J is located in this place. Therefore, the inverse element of U is letter Y. And to conclude the inverses of the elements that we have, so inverse of J is equal to J, inverse of O is equal to S, inverse of U is equal to Y, inverse of R is equal to E, the inverse of N is equal to N, the inverse of E is equal to R, the inverse of Y is equal to U, the inverse of S is equal to O, the inverse of 1 is equal to 1, the inverse of 2 is equal to 2, and the inverse of 3 is equal to 3, while the inverse of 4 is equal to 4, and the inverse of 5 is equal to 5, the inverse of 6 is equal to 6, and the inverse of 7 is equal to 7. And for the last one, the inverse of 8 is the inverse of 8 is equal to 8. And to conclude, the table under the operation star represent a group structure because it meets all the necessary conditions that define a group. First, the operations is closed, meaning the result of applying the operation of any two elements in the set is still an element within the same set. Second, the operation is associative, so the groupings of element does not affect the outcome. Third, there is an identity element, which, when combined with any element on the set, leaves the element unchanged. And lastly, every element in the set has an inverse, meaning there is another element in the set that, when combined with under binary operation star, the result is identity element. Since all these group properties are satisfied, we can conclude that the table defines a group. And that's all. Thank you for listening.